Hello, in this class we are going to look at superplasticity. It is again a material phenomenon that has impact with relative to the nanoscale, and so we are going to look at some background associated with this field, and then look at some experiments and ways to look at these experiments to carry out these experiments. And in that process look at the synthesis involved in the sample. We look at new way of synthesizing samples that have nanocrystalline structure, and also new ways of studying those samples. So these are things that we will look at. As I said, through this course we are looking at different phenomena. In the context of that phenomena, we are looking at different techniques that can be used, different analysis processes that can be used. So that is what we will do today. So our learning objectives for this course are to briefly look at superplasticity. You can look at courses associated with the mechanical properties of materials, where superplasticity is discussed in much greater detail. We are going to look at a very brief overview of superplasticity. In particular, I would like to bring out what is the difference between superplasticity and plasticity. So that is something that we want to spend some time trying to understand. I would also like to look at some models that people have proposed for superplasticity. How is this phenomenon happening at the material level that you see something in a macroscopic level. So this is the idea that we would like to pursue. Okay, so let us look at the idea of superplasticity itself. Generally this is looking at the possibility that you can have an elongation of 100% or even 1000%. What do we mean by that? So you do a tensile test. So you let us say you take a sample and you do a tensile test, and so let us say that is your dog bone sample. And then you do a tensile test on this. So as you start testing it, you eventually have some necking process. So initially you are only seeing elastic deformation, and then eventually there is some form of plastic deformation that is beginning to happen. Right. So some plastic deformation happens, and then you have some necking that is happening, and then eventually the material begins to expand. So we look at the final elongation. So finally the sample will be something that like that. Actually I need to change that. So something that looks like that, where finally you have a sample that is fractured, right. So you look at the final elongation that you have accomplished. So you have some gauge length, and then you look at the final length of that sample relative to your original length for that region, and then that gives you some idea of how much it elongated before it failed. So usually you are looking at several tens of percent maybe at most, which is where you will see this kind of regular plasticity behavior, but you are looking at elongation greater than 100% and sometimes even 1000%. There is even reports of 2000% elongation. So which means you take a sample and then you keep on elongated, very long sample it becomes before it fractures. So this phenomenon, once it was observed, was referred to as superplasticity, and it helps you get fairly complicated. It is a very important metal forming phenomenon, and you can use that to get some fairly complicated shapes when you do metal working for any particular purpose. And in all those cases, it is very important that the final shape is obtained without fracturing that material, right. So some complicated shape you want, some deep cup that you are trying to form and so on. You want that whole thing to form without a crack in the cup or some broken part of that cup. So that means it has to continue to plastically deform in that range over which you are deforming it, and that is where this superplastic deformation process really helps us. This usually occurs at a high what is referred to as a high homologous temperature, and this homologous temperature refers to the temperature of the sample relative to its melting point. So whatever is the temperature of the sample, let us say the sample is at temperature Ts divided by T melting point of that sample. So, if you are looking at half the melting point of the sample or even higher than that 0.6 Tm etc., then you say that you are at a high homologous temperature. This is very important because it is not simply the temperature that counts. The temperature, when we say something is high temperature or low temperature, that is always a relative statement that we are making, and it is relative to what? So, it is relative to this melting point, and the best way to bring that out is to look at it as a ratio of that temperature to the melting point, and so this ratio is your homologous temperature, and as long as this is more than 0.4, I mean more than 0.5, more say 0.6, 0.7, then you are saying you are at a high homologous temperature. And it is also seen that this happens at small grain size. So, this combination of this in general very high elongation and this deformation happens at high temperature, relatively high temperature, small grain sizes, this is referred to as structural superplasticity. So, this has got to do with the structure of that material and what is happening inside that material. This is called structural superplasticity. So, when you look at superplasticity in general, it is of these two kinds, structural and environmental, but for most applications we are looking only at the structural aspect of superplasticity. The environmental aspect of superplasticity is I mean, or that version of it is a version where a material is showing you behavior that looks like superplastic behavior, I mean which has all the, I mean this kind of very long elongation before failure, that kind of behavior it is showing you. But when they study it, they find that it has got to do with the fact that you are operating or cycling at temperatures very close to a phase change temperature. So, there is some phase change that is happening in that material, and presumably it may also be that phase change results in significant anisotropy in the property of that material, and if you are close to that range where this anisotropy is happening and you are utilizing this anisotropy to your convenience by increasing deformation in one direction relative to another direction, and in that process you see long elongations before failure. So, it seems to convey the kind of behavior that you associate with superplasticity. So, that is one way in which you can accomplish this near superplastic behavior. So, that is sort of to the extent that you see these large deformations, we call it superplastic in this context, and then it is because of something that is associated with the internal environment of that sample, and so we just call it environmental related superplastic behavior. However, for most engineering applications, for technological applications, which is something that we desire in material science and also in the context of this course, really the one that we are looking at is this structural superplasticity. This is the one that is more relevant for our discussion, and it is sort of associated with this smaller grain size and all these other phenomena that we saw here. Okay, so, this is what we will look at. Okay, so I already showed you something about the idea of what is happening when you deform the material. So, we will look at it a little bit more in detail, and then we will try to understand what is it that is happening that we can try to pin down and say that this is happening and therefore, it is superplastic. Okay, so we have to be a little bit more specific. Elongation is a much more generic term, and like I said, you could have 100%, you could have 1000% and so on, and so it is a very wide range. So, would you call 100% as being plastic and 1000% as being superplastic? So, where is that line of demarcation? And so, just looking at elongation does not convey to you a clear enough picture as to what is when you should call something as superplastic deformation. So, to look at it a little bit more, let us assume that you have this dog bone shaped sample that is being subject to a tensile test. Right. So, what would happen when you do a tensile test is that you are now applying a stress or a load in this direction and this direction. So, some load you are applying. So, L is the load you are applying, and if there is a cross sectional area A, then the stress that you are applying is L by A. That is the stress that you are applying, and if that is the cross section, that is here. So, there is some cross section that is out here, and we will assume that for that cross section you are getting the area A. Okay, so, let us say it is a rectangular cross section. In that case, you will have some cross section that looks like that, and that cross sectional area is A. Okay, so, from and that is the cross section if you cut the sample down. So, this is the stress that you are applying and you get a strain in this sample. Now, the strain is essentially whatever, I mean, even if you are looking at it as the engineering strain, then your it is the the change in length by the original length that you have there, and that is the strain that you are getting. So, now when you start straining the material for a fair bit of the, for an initial part of the straining process, where you start putting load on the material, when you start stressing the material, initially whatever strain you see is the elastic strain, at which point if you release the load, it goes back to its original length. So, you will have no change in length. Eventually if you increase the stress enough, then you start seeing plastic strain. So, initially elastic deformation is occurring, and that is by definition something that you can recover. When you remove the load, you get back your original dimensions, and then eventually once you cross the yield stress, plastic deformation begins to occur. Okay, so, this is what we would typically see. So, eventually once you cross the yield stress, plastic deformation begins to occur. So, now initially the plastic deformation is occurring throughout the sample, and then as you continue this deformation at and then this whole sample is beginning to go to a larger and larger length, and at which point if you release the load, it will not go back to its original length, but it will stop at some length, and that is the overall plastic deformation that you have accomplished. So, this is what starts off initially, then you get this plastic deformation, which is at that point uniform. Then what happens is, if you continue this stress strain experiment, and you continue to increase the load on the sample and therefore the stress on the sample, a neck begins to appear. Okay, so, this is a neck. You can see here that the cross sectional area here is distinctly less than the cross sectional area here and less than the cross sectional area here, right. So, if I call this A1 and this is also A1 and this is A2, and A2 is less than A1, these are cross sectional areas. Okay, so, you have a region in the sample where locally some thinning has happened, it has become thinner than the rest of the sample, and then if you now start putting the if you look at the load, if you maintain the load, so whatever is the load, so some load L you have, then you find that in the location 1, okay, so so this location 1 you have at excuse me, at 1 stress is L by A1, at 2 location 2 you have stress which is L by A2. So, clearly, so this is sigma 1 sigma 2 and sigma 2 is greater than sigma 1, and you will also find that the strain, the elongation that you are now doing, a greater fraction of the elongation is happening at this thinner region, because you have a necking that has happened, cross section is smaller. So, the thinning is this region, and therefore, the neck has formed in this region, and the strain, a larger fraction of the strain is beginning to happen here. So, the strain is now, the plastic strain that is happening is no longer uniformly distributed across this entire region. Okay, so, the strain is not uniformly distributed across this entire region, you have more of it in this region. So, this strain is happening over a period of time, right. So, if you look at it as a strain rate, which is the amount of strain that is happening per unit time, which is epsilon by T strain rate. So, we will define something called a strain rate. So, strain rate we will call as epsilon by time, the strain by time. Then if you have the same amount of strain occurring over the entire region, then the strain rate is the same regardless of if the strain is uniformly distributed across the entire length, then the strain rate is the same across the entire length, right. So, till the neck appears, this is true, till the neck appears, the strain rate is uniform across the entire length. Now, once the neck appears, you are having, even though you may get a total strain of some value, a larger fraction of that strain is happening at the neck than is happening over the entire than is happening over the rest of the length. Therefore, the strain rate at location 1 epsilon dot 1 is less than the strain rate that is happening at the second location epsilon dot 2, because more strain is happening in that region which is thinned relative to the region that is relatively broad. So, when the test is going on, one of the parameters that has changed is the strain rate. Once the neck appears, the strain rate at the neck is higher than the strain rate at the rest of the sample. So, this is a phenomenon that is happening. So, so this is your sample and this is how it is strained. So, if you see at the neck, epsilon dot which is greater than epsilon dot at the rest of the sample. Okay. So, the epsilon dot which is happening at the neck is greater than the epsilon dot that is occurring at regions away from the sample, and that has got simply to do with the fact that the region has become thin, stress is actually higher there, and the strain is no longer uniformly distributed. Okay. So, now given that this is happening in the sample, different samples respond differently to this situation. Okay. So, this is what happens. So, you have the strain rate that is getting higher at that neck, but different samples respond differently to this situation, and that is captured by this equation. Okay. So, this equation captures how different samples are responding to these differences in strain rate, and this is referred to as the strain rate sensitivity. This brings out what is called the strain rate sensitivity. Okay. So, this brings out strain rate sensitivity. So, what do we see here? We see here the yield stress sigma y, yield stress, and you have this strain rate here, right. So, this is yield stress, and this is strain rate. So, written this way actually it does not talk anything about the formation of a neck or any such thing. It simply says that the yield stress, normally when we draw a stress strain curve, we only see one yield stress, right. So, you will draw the stress strain curve. So, you see something like this, let us say it is an engineering stress strain curve. So, you see something like this. So, somewhere here is what we mark as our sigma y. right. So, yield stress is occurring there. So, we just mark one point on this curve and we say that is the yield stress. This equation suggests that actually that value sigma y that you will see depends on the strain rate that you are using, and that is captured by this equation with an exponent. So, this exponent tells how sensitive the strain rate the yield stress is in relation to the strain rate. Okay. So, it is generally found that for a lot of materials this exponent is small. So, you are looking at values distinctly less than say 0.1 for example, it is much lower values, but for some materials it is a much higher number. So, you are looking at values of 0.3, 0.4 something like that 0.3, 0.4, 0.5. So, if m is in the region of, if m is greater than say 0.3, so it is of the order of 0.4 or 0.5 etc., we say we describe the material as being a high strain rate sensitivity. So, the strain rate sensitivity of the material is high is the way it is described, strain rate sensitivity of the material is high. So, this is a phenomenon that shows. So, it means that if the strain rate changes, if the strain rate increases, the yield stress increases. So, if you do this experiment at low strain rate you get one yield stress, if you do it at higher strain rate you get another yield stress. Typically that at higher strain rate you will get a higher yield stress. The extent to which the strain rate affects the yield stress depends on this exponent. So, the higher the exponent, the greater is the increase in the yield stress for the same increase in the strain rate. Okay. So, now when you look at plasticity versus superplasticity, technically really the difference comes down to this exponent. Okay. So, if you have a high value of this exponent in the range of 0.3, 0.4, 0.5 something like that, if you have a strain rate sensitivity index being in that range, then we describe it as being superplastic, as a material that is actually being superplastic. So, when you get done with the analysis of the material, if you actually look at what you have I mean if you can do the strain rate sensitivity study and come up with a value for this index, and you find this index to be in the range of this 0.3, 0.4, 0.5 or that rate thereabouts, then we can use this as a indicator that this material is showing us superplastic behavior. So, other than having a very descriptive sense that you expand a material and then because you are expanding it to very large degree before it fails and you call that as being superplastic, and that is something that we cannot completely control because sample to sample you may have some variation and the percentages may change etc., and it is not something that we can really compare material to material as well. If you come down to bring it down to the strain rate sensitivity concept and you look at this exponent, using this exponent we are in a much better position to really say that these are all the materials that are showing a superplastic behavior, these are all the materials that are not showing us superplastic behavior. So, now why is this strain rate sensitivity index important? So, why does that convey to us that some material is going to be superplastic? How does it show us? How does it end up reflecting in a long elongation before failure? So, that is a point I think we need to understand. Why is it showing us, why do we say that if the index is high the material is showing a superplastic behavior? Because we normally simply associate it with long elongation before failure, right. So, that is physically that is what we see. From a model and theoretical perspective, we are saying we are relating it to this exponent m and saying that if that value is high you will see high elongation. So, why does that happen? So, that is something that we need to understand. So, to understand that let us go back to this idea that we just saw, that at the neck the strain rate is higher than at regions away from the neck. Okay. So, at the neck the strain rate E dot is higher than the strain rate at regions away from the neck for the same sample. So, you are at that sample, you are testing that sample and you have done elastic deformation, you have started plastic deformation, and as you are doing plastic deformation at some point the neck has formed, and when that neck forms we see that the strain rate at the neck is higher than the strain rate in the same sample at regions away from the neck during the exact same test at that same instant of time. So, now what happens is that if you go back to this equation here, so you have sigma y is some constant c epsilon dot power m. So, I will write that here. Okay. So, now we see here that the strain rate at the neck is higher than the strain rate at regions away from the neck. So, therefore, the sigma y at neck is higher than sigma y away from the neck. Okay. So, sigma y at the neck, the yield stress at the neck is now higher than the yield stress at regions away from the neck, because the strain rate at the neck is higher than the strain rate away from the neck. More importantly, when the strain rate sensitivity index is high, this difference between the yield stress at the neck and the yield stress away from the neck is also drastically higher. You have much higher yield stress at the neck relative to the yield stress at regions away from the neck. So, now what we see is that usually once the necking has started, it will continue to deform much more at the neck than at regions away from the neck, and so pretty quickly you will have failure, you will have a fracture. So, that is the way the general tensile test happens. For most materials, you start testing it, it starts undergoing some plastic deformation, neck forms, and then that is the region where more of the deformation is getting localized, and then pretty soon the material fails at that region. Now, when strain rate sensitivity index is high, what is happening is that once the neck forms, so once the neck forms here for example, so here epsilon dot has increased, relative to the rest of the sample, epsilon dot has increased, therefore, sigma y has increased, again relative to the rest of the sample, right. So, now if you want to do the next increment of deformation, where will the material deform? That is the question we have to ask. We have already formed the neck. Generally in most samples, if you once you form the neck, as you try to deform more of the deformation happens at that necking region, and therefore, the sample fails. When the strain rate sensitivity index is high, because it is high, the sigma y has increased at that region, therefore, it is more difficult to deform the sample further at the neck. Because the strain rate sensitivity index is high, the yield stress has increased at the neck, and therefore, this is happening during the test. This is not something that is happening independent of the test. During the test, the neck has formed and the strain rate has gone up at the neck, therefore, the yield stress at that instant has gone up for the region that is at the neck, and therefore, this region is more difficult to deform. Relative to this region, or relative to this region. You can see both these regions are easier to deform, these two regions are easier to deform. This is also easier to deform. Therefore, interestingly, even though you have formed the neck, the deformation is no longer easy to deform the neck further, rather you start distributing this deformation into this region. So, now you will form, so this region starts, this region deforms more, or preferentially the deformation happens in the region where raking has not happened. Okay. So, it is the opposite of what you would normally expect. Preferentially now deformation is happening in regions where necking has not happened, because there the strain rate is less and therefore the yield stress is less. So, wherever the yield stress is less, the stress is going to go to, I mean the sample is stressed the same degree, wherever the yield stress is less, the material is going to deform more easily. So, more deformation now begins to happen in this region and this region, more deformation begins to happen, and therefore the neck actually becomes more stable than the rest of the sample. What we are effectively seeing is a situation where the neck has become more stable than the rest of the sample, and so the deformation spreads across the entire sample, or you sort of the neck spreads across the entire sample. It does not deform more at the neck, but rather it sort of deforms over the rest of the sample, and so the whole sample now is capable of a very significant amount of deformation before that original neck actually starts seeing conditions where it has to now further deform. So, this is the reason why these materials that show you superplastic behavior are showing you that behavior as a direct result of this strain rate sensitivity index. And once you consider this concept, you understand why this material keeps expanding over a very long extent of expansion before it actually finally fractures. So, that is the reason why the strain rate sensitivity index is very important, and that is why this value of m greater than say 0.3, 0.4 something like that begins to indicate that the material is a material that is suitable for superplastic deformation, and that is the real difference between plastic behavior and superplastic behavior. That is the fundamental aspect associated with this. So, I think that is a background that is useful to have. Like I said, you should look at some a course on mechanical behavior of materials, where this is going to be described in much greater detail. A significant amount of work has been done on this, and so there is a lot of literature on it, there are a lot of books on it, book chapters on it. So, you should look at it if you want a much more elaborate discussion, but this gives you the background for it. Now, we need to look at what are these models for superplasticity. So, we have seen experimentally externally what is happening. Externally, like I said, you do this test and you see this long elongation, and then if you do some strain rate sensitivity index tests, you can also get a value for it. So, this is external. So, you sort of made some measurement from the sample, some numbers from the sample, and then on that basis we make some statement about the sample. We would like to understand what is happening internal in the sample, interior to the sample, that may help us understand what we are seeing externally. So, that is the point that we need to understand, and so we are looking at models for superplasticity, and really there are two different people have suggested models, and so I mean it is a phenomenon that is up for discussion. You can always think of different models, and it may even be that in different samples you see different models. But importantly, you tend to see these two models. One is called grain boundary sliding, which is I would say the most significant model that we need to consider, and there is also this idea of recovery and dynamic recrystallization at higher temperatures. So, we will briefly look at both these models and see what exactly we are looking at. So, if you look at grain boundary sliding, the idea is simply this. So, you have a lot of these grains. So, I mean of course, there is in this diagram I am drawing it kind of loosely, but there is no gap here. So, you have something, or maybe you have some porosity there, but that is not the we want something without porosity in fact. So, we will assume that these are close enough that you do not really have much of a gap there. That is sort of how this material is. So, now when you apply a stress, and let us say this is how the this set of 4 grains are perceiving the stress in the context of this testing, then a lot of things are happening. As you pull, normally we are talking of plastic deformation occurring because you have dislocations moving through the sample and through these grains, individual grains, and so then the shape of the grain itself changes. So, shape of the grain changes. So, that is a normal plastic deformation mechanism that we are looking at, where shape of the grain changes, and then eventually the set of grains change shape while they are still trying to maintain contact at the grain boundary, and then in the process the overall sample then elongates. We are now looking at a situation where, because of the way the strains are, stresses are, so this grain is trying to twist that way, this grain is trying to twist this way, this is trying to twist that way, this is trying to twist this way, and so on. So, you can have some kind of rotation, you can also have some possibility that you will have grains sort of slide through this through this. So, this top grain is sliding in this direction at this interface, and these two grains are sort of sliding in that direction. So, if you sort of look at this in let us say after a little bit of deformation has occurred. So, let us assume this is still your other grain there, and this is twisted down that way a little bit, and then this grain has come off here, and then the other grain is sitting here. So, if I call this 1, 2, 3 and 4, you now have 1, 2, 3 and 4. So, this is how they have slid with respect to each other, and this is because the stress is being applied in this direction. These two are being, the set of grains are being pulled apart, and they start sliding with respect to each other. So, this has got to do a lot with also how those grain boundaries are, what is happening at those grain boundaries, what are the sort of angles at those grain boundaries and so on, and what is the level of bonding at those grain boundaries. A lot of things have to be looked at for this to happen, but this is the model that has been suggested, that instead of individual grains deforming and then that deformation collectively resulting in the overall deformation of the sample, here we have a situation where grains are not necessarily deforming, but they are sort of repositioning themselves with respect to each other, individual grains, and as a result of this repositioning, a bunch of grains have shifted one way, bunch of grains have shifted the other way, and overall you see as so material has moved internally in the sample, and because material has moved internally in the sample, you see an external deformation. And it turns out that when you make the grain sizes smaller, this the probability or the potential for the material to show you this kind of rearrangement of atoms or sorry rearrangement of grains becomes much more significant. So, I have just shown you a hand drawn sketch, but let us just look at it here as a some kind of a model that I am showing you. So, here I have actually shown you deformation in the sort of the opposite direction here. So, let us say we have this set of grains that are being pulled this way and this way, and then you can have a situation where these 4 grains 1, 2, 3 and 4 and this is let us say 5, 6, 7 and 8. So, you had one directly above, I am sorry, you had one directly below 5, 2 directly below 6, 3 directly below 7 and 4 directly below 8. Now, with the application of some stress, you have this situation where you have 1, 2, 3 and 4, and you have 5, 6, 7 and 8. And so, clearly you can see significant rearrangement has happened. You have whereas 1 was previously below 5, it is now below 7, and previously 2 was below 6, it is now below 8. So, so this I mean as you can see here, this means that these I mean this is a simple simplistically drawn model, and the grains look large, and in principle it looks like the grains on top, the 5, 6, 7, 8 are sliding with respect to 1, 2, 3, 4, and for that to happen actually those top grains have to move up a little bit and the bottom grains have to move down a little bit and then rearrange, if we look at it as a macroscopic model with this kind of a drawing in mind. But in reality there is a lot of I mean sliding that is happening without this level of necessarily this level of gap formation. There is some sliding, there is some rotation, this diffusion occurring through the grain boundaries. So, it is a complex phenomenon that is happening there, and then this sliding is happening, but this model just what I am drawing here sort of captures the essence of what is happening there and gives you some kind of a summary of what will happen if a bunch of grains start sliding with respect to each other. And like I said, this is another drawing which probably gives you a better idea, because many times when you look at microstructure you may actually see situation like this rather than a very well defined situation like this. You are likely to see situations like this, and there is a lot of evidence and lot of studies that go into trying to understand which phenomenon is happening and in which material it is happening, and people keep refining these models. They try to give you variations on these models, and of course as you may imagine, when you look at a model of this nature and you are trying to say something with respect to locations of grains, often you would have to do a fair bit of electron microscopy for you to convincingly support one model in preference to another model. So this is something that we have to look at, and as I said, there is always this element of how the grains reorient themselves. They may not necessarily be oriented as well as they are in this image. This image is just a schematic which shows you 8 grains which are all of exactly the same size, and they are oriented in a certain systematic manner that you see here. In reality, this is not what you will see in most samples. There is going to be some grain size variation, there is going to be some, they are not necessarily going to be equiaxed in all directions. You will have a grain which is slightly longer in one direction, slightly longer in another direction, different sizes, and those different sizes are also going to be mixed. You will have like 2-3 small grains, 2-3 big grains, relatively speaking, and they are all going to be next to each other. So it is a kind of a complex situation that you have there, which you are trying to simplify in some sense and come up with a model. So which seems to which does not generalize so much that you have lost the essence of that sample, but still captures enough that you can say that this is probably what is happening in that sample, and you might have to give experimental evidence. So experimental evidence is actually very hard to give for this, because you have to do you would like to see the deformation as it is happening and watch the grains rearrange themselves. Increasingly with advances in what can be done with electron microscopy, and we will see that in our subsequent classes, you can actually study nanomaterials where you can see this kind of rearrangement that is happening. So this is grain boundary sliding, and variations, like I said, of this model are present, and it helps explain one part of I mean significant fraction of superplasticity is explained using this theory. There is also another theory, or at least maybe for some number of materials this is a better description of what is seen as behavior that sounds similar to superplastic behavior, and that is recovery and dynamic recrystallization at higher temperatures. So recovery is a phenomenon that is there in materials, which is primarily associated with reduction in defect density. So what is this defect? Defect is is all those dislocations that have been formed in the material. So you are doing deformation, you are deforming that material, and so dislocations or planes of atoms which are moving, or half planes of atoms which are moving, have now formed in that material. And the more you deform the material, more such half planes are formed, and they are all trying to move in different directions. A half plane of an atom is a higher energy state, and if you give it enough the right conditions, it will like to actually go back to being a full plane of atoms. Similarly, you are also deforming that crystal, so you are changing its shape, you are changing its aspect ratio, etc., usually also associated with increased energy and so on. So if you give it the right kind of conditions, which usually means a high enough temperature, the system would like to go back to a lower energy state. So normally, in fact, when we do metal working, metal forming for any application, you are doing some process by which you are changing the shape of that material, and let us say you have done plastic deformation, and you have, in that process you have introduced a lot of dislocations into the system. You have also changed the shape of the grains. Generally this is a high energy state, and it is also resisting further deformation, and therefore you feel much higher yield stresses have to be much higher stresses have to be applied for you to deform the material more. And in an industrial setting, that is not a nice thing to have, because you are wasting energy. You are spending a lot of energy if you have gone from if you have done say 5% deformation with some amount of energy, it would be nice to do the next 5% of deformation also with the same amount of energy. If suddenly the energy requirement is going up significantly, then your cost for doing the deformation goes up. So normally whenever you go to a industry where they are doing considerable amount of metal working or metal forming and trying to change the shape of that sample significantly, what they will do is they will do some amount of metal forming or some amount of change of shape, and then they will do heat treatment, which simply means they take that sample to a certain higher temperature, which will depend on the phase diagram of that sample. They take it to a certain higher temperature and wait at that temperature for those processes that have happened in the material to reset themselves. What do I mean by that? So, you formed all these dislocations, now those dislocations will recombine and you will now have full planes of atoms, and you have deformed this all the grains into some different, totally different aspect ratios. Those grains will again they are all under high energy states, and then you will nucleate new grains which are equally sized in all directions, equiaxed grains will be formed. This material which has lower defect density and also has grains that are equiaxed will actually have be now weaker than the material that you put in for the heat treatment. So, generally from a manufacturing perspective, this is a good thing to have, because you have taken a material and it has become harder to change the shape of the material. You were trying to change the shape of the material so that it is can be put to a certain application in a certain shape, final shape. Halfway through it you found that it is getting difficult for you to change the shape of the material further. By doing this heat treatment, you once again make it a softer material and you can do second round of changing of shape and get yourself to the final shape that you want. So, this is the general process that we do. So, we actually do heat treatment. Heat treatment is done specifically So, heat treatment is done to make the material softer, so you can continue to do the deformation. So, from a manufacturing industry perspective, this is good. However, this is generally not good from an application perspective if the application happens to be a high temperature application. It means that you have taken a material that is strong and you put it to use in some application, you did some test and you found that it has a certain strength, you assume that it has that kind of a strength and you put it into use in some application. However, because the temperature is high at that application, during that application, the material actually becomes weak during use, and therefore actually is able to handle only a much lower level of stress than what you tested it for, and therefore it fails. And so, this is not particularly great from the perspective of use, but it is particularly useful from the perspective of changing the shape of the material for some particular end use. And so, one thing that happens when you do this high temperature treatment is that there is a reduction in defect density, and also you have nucleation and growth that will occur at higher temperature normally, and both of these are being used as heat treatment processes to help you make the material softer and deform it further. Now, this recovery and dynamic recrystallization is a situation where this is happening alongside deformation. So, it is happening alongside deformation. Okay, so, alongside deformation it is happening. So, the point is, whereas in the heat treatment that I told you, this is a two-step process. You deform something, and then when you are done, you are finding that it is getting difficult to deform, you take it to a furnace, you put it in the furnace, heat treat it, make it softer, take it out, again put it on the machine, deform it further. So, this is the way you are doing normal activity. Whereas this is a situation where you are doing the deformation at some temperature, where this reduction in defect density as well as nucleation and growth of new crystals seems to be happening along with the deformation process at the same time. So, the material is you are deforming it, it is becoming stronger, then it is defect density is decreasing, recrystallization is happening, it is becoming weaker, you deform more, become stronger. So, these two are happening side by side and sort of working with each other, at the same time countering the effects of each other, and so the material continues to deform. And so, wherever the deformation has occurred more, like we saw with that necking situation, wherever the deformation has occurred more, the defect density is higher there, the grains have deformed much more there, greater chance that it will recrystallize there, the greater chance that it will recover there, and therefore this continues. And this is how you see another phenomena occurring in a sample which shows you something that looks like superplastic behavior. So, these are the two major phenomena, grain boundary sliding and this dynamic recovery and dynamic recrystallization. And these are all phenomena, as I said, lot of studies go on it. If you look at literature papers, many models are suggested which are maybe some variations on this, maybe greater variations on this and so on, but these are the kinds of things that are looked at from the perspective of superplasticity. So, in summary, the one major indicator of superplasticity is this high strain rate sensitivity, and that is the I mean sort of a true indicator of superplasticity. So, many times if you simply give a deformation number, that is not considered enough, an elongation to failure. If you just give that value, that by itself is usually not considered good enough way of indicating formally that you have got a superplastic material. Chances are it has high strain rate sensitivity, but people would prefer that you figure that out and you find out what is that strain rate sensitivity, and that is a much better way of indicating superplastic behavior. And many models have been suggested to look at superplasticity, but really the model that sort of I would say stands the test of time, or the one where maximum belief is there, is this grain boundary sliding, and it has been used to explain superplasticity as a way in which the deformation is occurring without necessarily having involving planes of atoms moving inside the grains, so without dislocations, or without the primary need for dislocations to be enabling this deformation, rather that the entire grains are sliding with respect to each other. So, that is our summary for today's class, the phenomena of superplasticity and the fact that it tends to happen under these kinds of conditions that we have described. We will look as we progress further towards experiments where we can look at it in the in relation to what is happening at the nanoscale, and also see what that data implies to at the end of it. Okay, so that's where we'll head with this. Thank you.